Hey everyone, so let's talk more about these limits that we are learning in class. So for some limits, we can do direct substitution, but I want to talk about some situations where this works, okay? So the first one is continuous functions, such as polynomial functions, are considered to be well behaved. Okay, and so what I want you to think about is, I'm going to scroll over here for a second, if a polynomial function could also be a linear function. So here is a graph of a linear function. So as I am approaching from this direction and as I'm approaching from this direction, they are going to meet, so therefore we are going to have a limit. That would be the same thing as a quadratic, okay? If I'm approaching from, let's say we need to get to this point, if I'm coming from this direction and someone else is coming from this direction, we are still going to meet at that point. So that is what it means by the polynomial functions are well behaved. So because we know that we're going to meet at that common spot from both directions, we can say that, hey, we can just substitute this in, direct substitution into the function and get our limit. But we do have to be careful on limits of discontinuous functions. So let me sketch one of those real quick. So if we have a rational function, so we have 1, 2, we'll put a vertical right here at x equals 2, okay? And let's say we are going like this way, and like this on this one, okay? If we did a direct substitution and we used our vertical asymptote, we're not going to have a limit because the denominator just became 0. But if we did a different number besides x equals 2, like 3, 4, -1, 0, we would be able to find something because they will be coming to that spot wherever we would choose. So you have to be careful with rationals, especially if the number that they're wanting you to find approaches ends up being a number that can be used for your vertical asymptote. So let's look at some of these problems here. So if you look at this first example I have, this is just a quadratic. So therefore we have a parabola. So therefore we could just go substitute it in. So we would have -1/2 4 squared minus 3 times 4 plus 7. Type that all into your calculator or do it by hand, and we would get a -13. So this is a quadratic. From a limit approaching 4 from both sides, we will come to a value. Okay. Here's example 2. So what type of function is a -2? Well, that is just your constant function. So we would go -2 and then draw a line. Okay. So as x approaches 3, so let me go draw a vertical line so that some of you guys could kind of see that. Okay. As we're approaching, okay, I like to talk to my students kind of about I have someone walking on this side towards this line. I have someone walking on this line towards someone. Are we meeting at the same spot? And yes, we are. Sorry, didn't mean to delete all that. Okay, so we are meeting at that same point right there. Well, what is that y value? And it's just a -2. Okay, so that one was just your constant function. Okay, let's go to the next one. Okay, so we have a crazy rational going on here. It even has a quadratic at the top. So as we're looking at it, I want you to compare this right here to this. Okay, if I plug in that 4, would I get a 0? Would the 4 match my vertical asymptote? And no, it does not. So that means we can plug this one in with direct substitution, and be able to get our answer of 19/3. Okay, and then here's the last one that I'm going to show you guys. If you look right here, there is what I'm wanting to know, the limit as it approaches a -3. Here's our denominator. Okay, does the -3 match up with our vertical asymptote? And yes, it would, because if I set this equal to 0, we would get x has to equal plus or minus 3. So therefore, if I'm approaching that vertical asymptote, then we know that the limit does not exist. Hope this helps you guys.